now, if I want to find the optimum x bar and y bar, it should satisfy the complementary staircase conditions. Okay. CS indicates complementary staircase. So I just write down the CS condition. So first of all, we have the first constraint multiplied by y1. The second constraint multiplied by y2. Right? First constraint minus, we move the right hand side. Okay. So first one is 5x1 plus 7x2 minus 35. So that's for primal problems constraint. And then talk about two problems constraint. Okay, so we want to solve. Okay, so we have four equations, right? And how many variables to be solved? Four. Okay. So four equations, four variables should be easy to solve, right? Probably not, because there's a multiplication. So sometimes we need to utilize discussion to check that not solve them correctly. Okay? Suppose we don't solve that. Suppose I give you the following information. Okay, suppose I give you this information, y1 star and y2 star is 0 and minus 3. The optimum solution of the minimization problem. So I want to ask you. First question is that what are the optimum solutions of suppose I give you the y star. So I will ask you to solve for x star as the optimum solution for the problem. And And also I want to, because I can plug in into the y, into this 4 equation, and I can find the x. The next thing is that I want to ask you that if this information is true or not. Okay. First of all, we want to plug in this value into this information, into these equations. So it means that I just change. Here I write down this equation because based on this. Right? So if I run out, I change the notation. It says star is the optimum solution. It means that I have to change. But to find the star, actually it's the same. Just utilize different mark or different notation. Okay. Based on this. Just change. Because so when I plug in the y to find x, how can I make sure the x is the optimum solution?
Z value and Z value is
It's the same. Z value and W value is the same. I should show you another problem. If you have time, go back to check the simplex method. Because right now, if I just give you this example, I have to show you again from very beginning. For the simplex method, you will find from the initial iteration and then goes to a second iteration, goes to final iteration until you find optimum solution, right? Okay. But if you go back to check that, you will find that in each iteration, no matter what if it is optimum solution or not, in each iteration, for the right hand side, give you. Suppose we solve for the maximization problem. The right hand side give you a solution for your maximization problem. And the row 0 will give you the solution for the y for the dual problem, right? It's a pi or y bar, y star. Okay. You will find in each iteration. Suppose you have a y here and you have x here. You will find that. You will find that in each iteration, the wy bar is equal to z. Not just in the optimum solution. But in the previous discussion, we show you that in optimum solution they have this scenario, right? But when you go back home to check, try to check because you already from the previous homework you already solved for simplex method, right? For each iteration, you can find. That's what you already have. And based on today or previous weeks, we can find the solution for the dual problem. And you can find that in each iteration, the W of y bar is equals to C of x bar. So does that contradict to what I have, or I'm telling you the wrong story?
I think it's
I'm telling you it's not true. Okay, well you can check that. Today you already have your homework, right? You have your homework back. You just check not optimal iteration. You will find its result.
because the minimum problem is for searching for the upper bound and the maximum problem is searching for lower bound.
Mm-hmm.
So they should only reach the optimum while there's
That's for the optimum solution. That's for optimum solution. I said because our previous discussion is based on optimum solution. But right now I tell you the story. No matter what in which iterations, you can find this result.
Maybe it is related with the constraints. So the solution, if it is not optimal, the solution will be infeasible for the problem.
Yes. Infeasible. You notice that in each iteration, the x should be feasible, right? Because when we apply the simplex method, it will always feasible. And based on this feasible, we go to find optimal solution. And we only take from our previous discussion for duality, we only talking about the final table. In the final table, we have this result. And in the final table, we can guarantee the y bar also feasible. Okay? But during the process, for the previous non-optimum iterations, we still can find y bar in the row 0. Okay? And we still can find this result. However, y bar is infeasible. Okay? When we didn't go to the final table optimum solutions, we still have this result. However, the y bar is infeasible. Check that. When you already have the homework. I probably will mention that later, but check that. Maybe I forgot. I mentioned that I mentioned this result when I'm teaching the operations research in undergraduate. So sometimes I suppose you already know that. So we're just talking about the idea. So for these 4 equations, just tell me this result. Just tell me that W of y bar is equal to C of x bar. But as what I said, if I didn't care about if it is feasible or infeasible, I probably find the solution here. And it is not optimal solution. So not just following these 4 equations, I also have once I solve these 4 equations, I can find the x1, y1, x1, x2, y1, and y2. When I solve for it, I have to plug in the x1 and x2 into the maximization constraint to check that if it is feasible. And when I solve for y1, y2, I have to plug into the minimization problem to check that if they are feasible. Okay? So simply just say that I only tell you that. But remember that in the very beginning, I already tell you that x bar and y bar they are feasible. Okay, so I just have to solve for these equations. So if I give you any example, so I give you an example like this. So you probably say, okay, I just solve for that, and you forgot feasible solution here. So we not just solve this equation, we also have to guarantee the result x1 and x2 and y1 and y2 should follow constraint. Okay? Check that. You go back and try to check that. If my argument is correct, if my mention is true or not. Okay? So following this discussion, so we start from this information. I already give you y1, y2. So I will utilize y1, y2 to find the value of x1 and x2. So since y2 star is not equals to 0, y2 star, here y2 star is minus 3. So I already know it's not equals to 0. So what information do I have? If I know y2 star, y2 star is not equals to 0, so the x1 right? Okay. Based on this information, I know it should be like this. Okay. Okay. So it means that the second constraint is binding. Becomes equality. But as what we know, the feasible you should follow in the feasible solution. So when we find x1 and x2, we should follow this constraint. So the feasible okay. Okay. So you can find. You can draw a figure because there's only two variables. That's less than or equals to 35. Okay. But it's the blue part is x1 minus x2, 2x2 is equals to minus 2. Okay, so it should be in this line. Okay, and however, the optimum solution is so the x optimum solution 0, 1 is this point. And this 56 divided by 17 and 45 divided by 17 is this point. When we have multiple optimum solutions, actually you can only find corner point feasible solution, right? And that's the corner point feasible solution, and that's another corner point feasible solution. Please still remember when we can find multiple optimum solution, and the 9 connecting these two corner points is our multiple optimum solution. Okay. So one way to that's what we that's for A. And if you want to make sure if this information is true or not, you can solve using simplex method. You use simplex method to solve. Also solve for it. You can make sure the information is true. Okay. Okay. Questions? Actually, that's the extension of the duality, because we already know because the duality let me know we construct the relation between the primal problem and dual problem. Once we know the dual problem, I can utilize another way to solve for the optimum solution. So this complementary extent is actually another way to solve the optimum solution. Okay. And I give you this example is that it looks easy if I just give you 4 variables and 4 equations. It looks easy to solve for that. But if we have more variables, it's not easy. Okay? So one way to find it actually is maybe if it's easy to find the optimum solution for the dual. So I can find it first, and then utilize this information to find, based on this complementary things, to find the solution for x. If it's easy to find the value of x, and then I plug it into that to find the value of y. Okay. If it is not so easy to find x and y, maybe I have to utilize this kind of discussion. Suppose I already know some variable is equals to 0, or it's not equals to 0, then I will know that the corresponding constraint is binding based on this equality. So for this scenario, I don't have to consider y, y2. I only have to consider 2 variables based on this discussion to find our values. Okay? Okay. Question so far? No, we want to probably I will go to the next topic. And the next topic, yeah.
So that means if one solution of the dual solution is not equal to 0, it must ultimately be that one is binding.
Yes. If an I goes to 0, it means that binding. That the corresponding constraint is binding. You know the shadow price. Binding indicates that, for example, That's our objective function. So it means the optimum solution is here. So for the optimum solution, this constraint is binding, this constraint also binding. Okay? For the shadow price it means that when I move this constraint further, my objective function value increase. Right, that's a shadow price. Remember that? And actually, the y is the shadow price. Okay, y actually is the shadow price of which constraint. I didn't mention that here. Because I mentioned that in undergraduate. And you probably already forgot about shadow price. They only know that, okay, I mentioned about shadow price. So if you have time, go back to check. It's impossible to detailedly to explain everything in the graduate course. So any other?
Shadow price. Sometimes we call shadow price as price.
Dual price or shadow price, yes. Why we call it dual price? Because there's dual problems available. Okay, you probably for some software we call it dual price. Any other questions? Don't worry about it. Actually, they are very related to each other. Yes. Because she asked me the question, so that's why I tried to answer. If I didn't tell you anything about the shadow price, don't have to worry about it. But I encourage you to review that, and you will find they are related to y. Because in the very beginning, I only solved for x for the primal problem. Okay, and the dual, the y actually is the shadow price. Okay. Looks like I will not mention about the shadow price. I will not. And I will not. That's another story. Should I tell you more about? In your simplex method, you have original variable and a select variable. Suppose we solve for maximization problem. An optimum solution. Objective function coefficient T, or the objective function coefficient of select variable is the shadow price. And also, that is the solution of your problem. Okay. Why? Remember that the C bar is equals to pi a minus c. That's what we mentioned previously. Okay? So let's talk about the snake variable. Let's talk about previously we distinguished them to CV and CN, right? Okay. Right now we talk about slack variable. Only for slack variable. So for slack variable, it means that right, only for slack variable. For pi, for the CV, I changed it, added the index CV by A B in the CV, right? Okay, so we can utilize the same way to talk about it. So slack variable. Slack variable. S is equals to I, identity matrix, in the CS 0. Okay, so you will find that CS bar is equals to pi. Okay, so in the optimum table, the slack variable's fit function coefficient actually is the solution of the dual problem. Okay. I'm not sure. Should I tell you that? Should I tell you this or not? Should not tell you this, because if I didn't systematically to tell you everything, sometimes it will confuse you. You will feel headache. But I just try to tell you that you learn linear programming long time ago. Probably you find it topic by topic. I just try to tell you that they are very related to each other. Okay. Okay, that's sensitivity analysis. Normally, I would try to talk about or provide an example actually based on maximization. And actually, if I utilize minimization, it also have the same result. Okay, so in most of the time, I prefer utilizing maximization as our example. Okay, so previously, you will find that I say maximization Z is equals to CX. Result is D. And then AX equals to B. So I already have a automatic form and I try to solve it. Okay? Okay. Why here I have plus D? If I talk about from the very beginning, the objective function value is actually 0. From the initial solution, actually 0. But as you know, the table we will probably have many tables to find have many iterations, because the table corresponding to each iteration. And in each iteration, we have the right hand side a Z value. Okay, so D indicates that for any iteration. So here actually is for arbitrary iteration, maybe not optimal, maybe optimal. Okay. So for in each iteration, we can construct the table based on the basic variable, right? So we can construct the the constraint coefficient A bar based on right. That's why, because based on our previous revised vector method, as long as I give you a vector variable, even I just give you a vector variable, you can construct a table for me to check if it's optimal or not. Okay? So based on this vector variable, I can construct A bar and also okay. Here is the pi A minus C, just mentioned. And we also can find, that's for objective function coefficient. For the right hand side, and I also can find the objective function value, which is plugging this into E. So we have I just plug in this value into E. Okay. So the table. So from the table, I can find A bar by this equation. You can find C bar by this equation, B bar by this equation, and D bar by this equation. That's what we already know. So that's why I said recall. That's from our previous discussions. Okay? And right now, we want to utilize what we already know to talk about sensitivity analysis. Okay, the reason of why we need sensitivity analysis is that, say, suppose there's an original problem. And maybe I kindly, in the midterm, I just give you flexible. You probably spend 10 or 20 minutes, you can calculate it's A bar, C bar, D bar, and B bar. Tell me that it is optimal or not. After 10 minutes, I tell you that I'm sorry I give you a wrong problem. I have to change the coefficient of that. What will you do? You probably try to curse me. So if I only change that, if I didn't utilize sensitivity analysis, probably I have to solve it again. I have to calculate everything again, right? But if I know how to utilize sensitivity analysis, actually I don't have to solve every part of this table. I only solve for something related to the coefficient or maybe the right hand side. I change. Okay, so that's why the importance of the sensitivity analysis. Okay, that's actually that's the purpose of the sensitivity analysis. Detailly, we will mention that later. But before we do that, say I can give you any Bexy variable. And based on this Bexy variable, we can find AB. Based on AB, I can find AB inverse. And how can I guarantee it is the optimum solution? How can I guarantee AB is the optimum basis? First of all, AB should be non-singular. Non-singular, what I mentioned that, right? Non-singular. Why non-singular is so important?
It has the inverse.
If AB is non-singular, then we can find AB inverse. Okay? And how can I guarantee it is optimum? Because I can find the C but greater than or equals to 0. So that's the optimum solution. And also, right inside, because here, all of the variables should greater than or equals to 0. Okay? So it depends. It depends on the problem I define. Here I say all of the variables should greater than or equals to 0. So the optimum solution, the B bar should be greater than or equals to 0. Okay? So observation is actually based on our previous definition. If AB is non-singular, so we can find the AB inverse, and we can utilize the AB inverse to help us to find the right-hand side value, B bar. And B bar actually is the basic variable solution. Okay, basic solution. Okay, so right inside here, B bar actually is the basic variables solutions, and the non-basic variable is 0. Okay. Okay. So furthermore, if I find that AB actually is the optimum basis, so it means that XB actually is the optimum solution. Okay. And the X bar is feasible and optimal actually is the definition of optimum solution. If I find an optimal solution, this solution should be feasible. Okay, and optimal. In this case, I can utilize the AB inverse to find pi. And the pi is the solution for the dual problem. So let's extend from not extend, actually is the result from the derivative. Okay? So that's why I say from the revised simplex method, I can give you any arbitrary basic variable you can construct. table of that. And once we know it is, once we know the C bar is greater than or equals to 0, and we also can find pi, the optimum solution for the dual problem. Okay. Questions? Next week we will continue for detailedly to talk about sensitivity analysis, and I will utilize an example to explain several cases. Okay. So next week I will start from the example and mention about several cases. Any questions? See you next week.